This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Okay, guys, I think we should start. So, welcome to lecture 14. So, in the previous lecture, we looked at a cylinder flow, right, where we have a uniform flow, a doublet, and also now we have added a potential vortex, which gives us a flow over a rotating cylinder. Right. So, remember we started off with 4 simple building blocks, right? A uniform flow, a potential vortex, a source and a sink. And a source and a sink, which is superimposed, gives us a doublet. All right? And if I combine these 3 flows, we get a flow over a rotating cylinder. Right? So we found the complex potential for this flow. Right? Well, we basically did this exam question, right? And we found the complex potential for the flow, right? And we also found that this parameter gamma over 4 pi u infinity a is important in determining the location of the stagnation points, right? So when there's no circulation, basically the flow it's just a flow over a cylinder, all right? And we have 2 stagnation points at the front and at the back of the cylinder. Now, when we increase our circulation, right, when gamma is non-zero, we observe that the stagnation points are located on the surface of the cylinder, but at an angle of theta measured from the horizontal, right? So when this parameter is less than 1, we see that the stagnation points are on the surface of the cylinder, but as we increase gamma, right, they are located at larger angles of theta, okay? Right, and this is the critical point when the parameter gamma over 4 pi u infinity a is equals to 1. We only have a single stagnation point located on the cylinder, right? Now, if we increase the parameter further, all right, or if we increase the circulation relative to our free stream velocity, right, so if we spin it even further, you can see that the stagnation point has detached from our cylinder. Okay, and then we have 2 stagnation points occurring, one occurring inside of the cylinder and one occurring away from the cylinder. Okay, and as I increase circulation even more, right, or increasing my parameter even larger, you can see that the these stagnation points are further and further away from the cylinder. Okay, and you can see that this region here, this region of fluid here, is totally unaffected by the uniform flow, right? Yeah, it's in its own bubble here, right? It's just circulating around here. Okay, and it looks like your uniform flow is no more horizontal. Okay, but actually, if you zoom out, right, your uniform flow is still horizontal, but just very close to your cylinder, you can see that the strong circulation by the potential vortex is affecting the streamlines quite a bit. Right. Now, there was 2 questions, I guess, or 1 question in the previous lecture where a student asked me, how do I know that one of the points are located inside, one of the stagnation points are located inside of the cylinder. Right, so if you are that student, okay, this is for you, right? Okay, so we know that R is greater than A. Well, we know that one point is located at R greater than A, right, which is not on the surface of the cylinder, and one is less than A, right, which is inside of the cylinder. But you guys weren't convinced with this part here. All right, so starting from, we know that gamma, the magnitude of gamma divided by 4 pi u infinity is greater than A, okay, right, that's just from, that's just from previously, right, here, okay, you know that. So, I'm just going to say, let gamma over 4 pi u infinity, right, to be equal to A plus delta A. Right, and A plus delta A is greater than A, right? So it's just some change in A, right, delta A. Okay, and if I substitute it back into this equation here, right, I'll get, this term is going to be A plus delta A, plus minus the square root of A plus delta A squared, right, minus A squared. Okay, and if I simplify this equation a little bit, all right, the A squared cancels off. I'm going to get A plus delta A plus minus square root of 2A delta A plus delta A squared. Okay, and I hope everyone agree that this term here is bigger than this term here, right? Everyone agree this term here is bigger than this term? Yes? Yep. Because I have this additional 2A delta A term here, right? So this term is going to be bigger than this term. Therefore, one solution has to be inside the cylinder. Okay? Right, and if you're the student who asked me, can you all nod your head? Yes? Yes? Okay, good. Right. So, hopefully that clears that up. Right, okay, so going back to the slides. Yep. And we have also proved that our cylinder remains a cylinder when we change the parameter gamma and u infinity, right? And because we have shown that psi, which is equal to 0, is a constant, therefore our cylinder is unaffected, right? Okay, so the next thing we want to do is to find the pressure distribution on this flow over rotating cylinder. Right, so remember that Cp is equals to 1 minus Vc, which is the velocity on the surface of the cylinder, squared, divided by u infinity squared. Okay, so we've derived this in previous lectures, right, for a flow over cylinder. Okay, and therefore it's very easy to find Vc squared if we start from our complex potential function. Right, so let's try and do this together. And if you guys can't remember, I'll just write a short note here. So Cp equals to 1 minus Vc squared over u infinity squared is derived from, right, hopefully you should know your pressure coefficient, which is P minus P infinity divided by half rho infinity u infinity squared. And also using Bernoulli's equation, right, where P minus P infinity equals to, you guys should be able to find that out, right? Okay, and that's how I express my Cp in terms of velocities, right, using the pressure coefficient definition and Bernoulli's equation. Oops. Okay, so to find our velocities, we want to work in cylindrical coordinates. Okay, and velocity in cylindrical coordinates, it's exponent I theta dw dz equals to ur minus I u theta. Oh, u theta. Okay, and you get negative u infinity cos theta minus a squared over r squared cos theta minus I u infinity sine theta plus a squared over r squared sine theta. Plus gamma over 2 pi r. Have I showed this already? Yes. Okay. Right. So you guys know this already. Sorry. And just very quickly. So we know that this is the real part. Okay, which is UR. Okay, and this is the imaginary, which is U theta. Yeah, I thought you guys have done this before. Right, so at the surface of the cylinder, what must we replace? What must we replace R with on the surface of the cylinder? You guys saw it. What must you replace R with on the surface of the cylinder? A. Good. Alright. Because A is the radius of your cylinder. Okay? Oops. Right, so therefore, if I substitute R with A, I'm going to get UR is equal to 0, right? And U theta is going to be equal to 2 U infinity sine theta plus gamma divided by 2 pi A. Okay, so just a bit of a comment. So the cylinder is a streamline. Therefore, radial velocity is 0 as expected. Right? Because you can't have velocity perpendicular to your streamline. Right? So UR is 0, which is good, because it's a streamline. And if you look at U theta here, we have two terms. Okay? And hopefully you can see that this term looks quite familiar. We got this term before, right? For a flow over a cylinder. Right? So that's a flow over a cylinder. Okay, and this additional term here is due to your potential vortex. Oops. Okay, So the extra terms has circulation due to your potential vortex. Okay? Right, so we have u r u theta, we can then find vc squared. So vc squared is basically just u theta squared plus ur squared, and we know that ur is 0, so we just get vc squared equals to u theta squared. Okay. Okay, so if I expand this term here, I'm going to get 3 terms. So it's going to be 4u infinity squared sine squared theta plus 2u infinity gamma divided by pi a sine theta plus gamma squared divided by 4 pi squared a squared. Okay, and I'm going to call this equation 2. Okay, and equation 1 is just my Cp. Cp is equals to 1 minus Vc squared over u infinity squared. Right, so now I just substitute equation 2 into equation 1. Okay, so I'm going to get Cp is going to be equal to 1 minus 4 sine squared theta minus 2 gamma u infinity pi a sine theta minus gamma squared divided by 4 u infinity squared pi squared a squared. Oops, oh, sorry. Oops. Okay. Okay, and again, hopefully you can see that this one here, what flow is that? 1 minus 4 sine squared theta. We have seen it before. There's a flow over a cylinder, right? Okay, that's just a flow over a cylinder, right? A non-rotating cylinder. Right, and all these extra terms these are due to my point vortex or potential vortex, right? Okay, is there any questions before I move on? Did I make any mistakes? Anything you don't agree with me? All good? Okay, so hopefully you can see from this equation here, Cp comprises of just your standard flow over cylinder plus this extra circulation terms, right? So when gamma is equals to 0, you just get back the standard flow over a non-rotating cylinder. Okay? Okay? Right. So okay, so if I were to draw my streamlines and also plot the pressure coefficient on the surface of the cylinder, all right, as you can see, when gamma is equals to 0, it's just a flow over a non-rotating cylinder. Okay, but as I crank up my circulation, or as I increase gamma, right, you can see that the pressure coefficient at the top bit of my cylinder is very low, okay, compared to the bottom. Right? So this difference in pressure coefficient at the top and bottom of my cylinder is going to generate lift, right? It's going to generate a net force. In this case, it's a lift upwards. Right? Okay, so consider lift force acting on a small element on the cylinder. Okay, so that small lift dl, okay, which is acting on a small surface there, okay, is just going to be equal to negative P, right? Negative because pressure is in a downward direction. P times A, right? A is the radius of your cylinder. D theta times 1. 1 is just a unit depth because this is a two-dimensional problem. Times sine theta, right? And it's because you want to, you are only looking at the vertical component of the force, all right? That's why you multiply it with sine theta, right? Okay. Right, so if I integrate over the whole cylinder, right, I'm going to get then the net lift or the total lift acting on that cylinder. Okay, so I'm just going to integrate it with respect to theta between 0 to 2 pi. Okay. Right, so using this information, we can then derive an equation for lift. Okay, so lift is just equals to negative the integral from 0 to 2 pi P A sine theta d theta. Okay, I'm going to call this equation 4. Right, so we know that Cp equals to P minus P infinity. Sorry, let me just over half rho u infinity squared. Let me just be consistent and use capital P. Okay, so from my Cp equation, I can rewrite it to find my pressure P, which is just half Cp rho u infinity squared plus P infinity. Okay, I'm going to call this equation 5. And I can also find, or I can also have not only lift, but lift coefficient, right? Which is just Cl equals to lift divided by half rho u infinity squared. which I'm going to call equation 6. Okay, so the first step is I'm going to substitute equation 5, this equation here, into 4. Right, so I'm going to get lift is equals to negative 0 to 2 pi, integral of 0 to 2 pi, half Cp rho u infinity squared plus p infinity a sine theta d theta. Okay, and to calculate my lift coefficient, all right, all I have to do is just substitute 7 into equation 6. There's going to be a lot of substituting. Right, please bear with me. So sub 7 into 6. Right, so I'm going to get CL equals to negative integral from 0 to 2 pi Cp plus 2 p infinity over rho u infinity squared. Okay, so I simplified the equation a little bit. Okay, times a sine theta d theta. Okay, and I have equation 8 here. Okay, now we already have an expression for Cp, right? Yep, that's just equation 3. Okay, so we want to substitute equation 3 into equation 8. Oops. Okay, so we substitute equation 3 into equation 8. Okay, and you're going to get a bit messy, all right? You're going to have a lot of terms here. But please bear with me. It's very important. Okay, so you're going to get, sorry. So CL is now going to be equal to negative integral 2 pi 0, 1 minus 4 sine squared theta minus 2 gamma over u infinity pi a sine theta minus gamma squared over 4 u infinity squared pi squared a squared. I'm just going to continue at the bottom here. Plus 2p infinity over rho u infinity squared a sine theta d theta. Okay, everyone agree? Right? Oh, it's a long one. Okay, so I'm going to factorize this equation a little bit. How do you integrate this mess? So you have to factorize it a little bit, okay? Make it look a bit nicer. So I'm going to factorize, I'm going to clump all the sine theta terms together, okay? So I'm going to have 1 minus gamma squared 4 u infinity squared pi squared a squared plus 2 p infinity divided by rho u infinity squared okay, plus everything else. So it's going to be, which is minus 4 sine cube theta minus 2 gamma over u infinity pi a sine squared theta. Okay, and all of this is multiplied with a d theta. Okay, everyone following me so far? Yep. So the integral of sine theta is easy, right? So we know how to integrate this, but these two terms are a little bit tricky, right? Sine cube and sine squared. So you have to expand this using your trigonometry identities. Oops, how do we do that? Oops. Right, so you need to expand this term expand using trig identities, okay? Okay, I'm going to skip a few steps, but hopefully all of you should know how to do it. All right, if you don't know, please try and do it yourself at home. Okay, so now I get an equation which has my sine terms again. Oops. 1 minus gamma 4u infinity squared pi squared e squared gamma squared plus 2p infinity. Okay. Minus, now I'm going to get 3 sine theta minus sine 3 theta minus gamma over u infinity pi a 1 minus cos 2 theta oops. It's going to be AD theta. Okay, so hopefully you all see that I've just converted sine squared theta to 1 minus cos 2 theta. Right, but this sine cube theta here, there's a bit of steps which I've missed, but you should get 3 sine theta minus sine 3 theta. Okay, for this whole term here. Oh, that's right, that's still there. Yep, that's still there. Okay, so now you guys are going to tell me, all right, the integral for this of these terms. So if I integrate sine theta, I'm going to get minus cosine, right? Okay, so the minus with the minus cosine gives me just cosine theta, all right? And if I integrate cosine theta from 0 to 2 pi, that's just going to be from 1 to 1, right? So it's just going to be 1 minus 1, which is 0. Okay? So all the terms just goes to 0 for this case, for this term, right? All the terms go to 0 for cosine theta. Okay, and then I'm going to get minus. Now I'm going to integrate again sine, so that's just going to give me 3 cosine theta minus cosine 3 theta over 3. Okay, and again, this is just the integral. If I integrate this from 0 to 2 pi, that's just going to give me 1 minus 1 again. Okay, so that's just going to go 1 minus 1. So does this term as well. So it's all 0 basically. Okay, and I have my final term here, which is plus gamma over u infinity pi a. Right, and if I integrate 1, I'm going to get theta minus sine 2 theta over 2. And I'm integrating from 0 to 2 pi. Okay, and sine 2 theta from 0 to pi is just going to be 0, right? Because sine of 0 is 0, sine of 2 pi is also 0. Okay, so I only actually end up with this term here. So I'm going to get CL is going to be equal to 2 gamma over u infinity. Okay, is everyone following? Yep. Or, alright, so that's CL. If I want to calculate the force, the lift force, it is then just equals to half rho u infinity squared CL. Okay, which will give me rho u infinity gamma. Okay, and this is just lift per unit length. Okay, because this is just two-dimensional, so it's per unit length. Okay, and you can refer back to your lecture notes in page 63. Okay, is everyone clear so far?
Does this mean if we don't have circulation, we will not have lift?
Exactly, right. So if there's no circulation or if there's no uniform flow, you have no lift. Okay, so remember, if you just have a uniform flow but you have no circulation, it's just a flow over a cylinder. right? And the pressure coefficient at the top and bottom are symmetric. So the net lift is 0. It cancels out. Okay. Right, now I have, I promised you some interesting videos, right? So let's see if we have them. Oops. All right, so this lift, which is caused by rotation, is known as the Magnus effect. Okay, so here we have a sketch, a photo of a rotating cylinder. Okay, we have uniform flow from left to right, and this cylinder is rotating clockwise. Where do you think is the lift, the direction of the lift? Is it going to be at the top, towards the top, or towards the bottom? Top, right? It's going to be upwards. The lift is going to be to the top. Okay, and if I superimpose the streamlines on top of this photo here, you can see that the stagnation points are located on the surface of the cylinder at some angle theta. Okay. But as I ramp up my circulation, or if this cylinder starts to rotate even more vigorously, right, you can see that the flow, the streamlines look a bit different, and the stagnation points occurs away from the surface of the cylinder. Okay. Right, so in theory, rotating cylinders can generate very large lift, but a cylinder is a bluff body, right? So you're going to have high drag as well. So you can see that they have placed these vertical cylinders on top of these ships to help generate some kind of thrust or forward movement, right? As when you have crosswinds, right? When you have crosswinds, and if your cylinders are rotating in the correct direction, right, you can have forward motion, right? And here's another example where there's 4 of them. Okay, so where's that? I can't remember which is it. I think it must be this one. Okay.
An der Emsmündung. Von Weitem sieht es aus, als hätte es 4 Schornsteine, wie ein Dampfschiff. Doch die Entwickler des E-Ship One nutzen eine noch viel ältere Antriebskraft, den Wind. Dieses weltweit einmalige Frachtschiff segelt.
Sicherlich sind das keine gewöhnlichen Segel im herkömmlichen Sinne, aber
Alright, so you can see the ship here with 4 rotating
die
cylinders.
nutzen, um das Schiff voranzutreiben. Also würde ich das auch als Segeln bezeichnen.
Die Konstrukteure des E-Ship One machen sich ein Phänomen zunutze, das bereits 1852 beschrieben und nach seinem Entdecker Heinrich Gustav Magnus benannt wurde. Die 4 Zylinder werden durch Elektromotoren in Rotation versetzt. Der Wind wird auf der einen Seite beschleunigt und auf der gegenüberliegenden Seite abgebremst. Dadurch entsteht eine Geschwindigkeitsdifferenz, die entsprechend den Strömungsgesetzen einen Druckunterschied ergibt. Und daraus entsteht dann eine Kraft, die quer zur Windrichtung wirkt. Die sogenannten Flettner-Rotoren des E-Ship One nutzen diesen Effekt für den Vortrieb des Schiffes. Ausgeklügelte Steuerungstechnik stellt das reibungslose Zusammenspiel von Segel und konventionellem Antrieb sicher. Bei der Konstruktion des Schiffspropellers konnten die Ingenieure auf Know-how aus dem Bau von Windkraftanlagen zurückgreifen. Die Ruderanlage wurde für die Fahrt unter Segeln optimiert.
Alles ist darauf abgestimmt, möglichst viel Energie einzusparen. Und das rein theoretische Potenzial, das betone ich immer wieder, liegt irgendwo so vielleicht bei 50%.
Frachtschiffe verbrauchen weltweit ca. 280 Millionen Tonnen Öl pro Jahr. Das E-Ship One ist ein erster Schritt auf dem Weg zu einer erfolgreichen Energiewende in der Schifffahrt.
All right. Like that video? So, yeah, there's other examples as well, right? So here we have an aircraft, okay? And instead of having wings, you can see that there are rotating cylinders, right? Which is used to generate lift. Oops. Okay. Here's another example as well. You can see that there's these large cylinders here instead of your wings. Okay, and another one here which is made by NASA, right? They're testing a plane by NASA, and you can see, if you look very closely, that there is a cylinder there. Don't know whether you can see it. Right, you can see a cylinder there. Right, and this rotating cylinder is used to generate lift for the aircraft. I have another video, not in German this time. a very old video. Oops, what's going on? Okay.
Frank Kawasaki competition for the heavy freight market may come from a young design group in Ottawa, Canada.
The space community doesn't know what to make of it on the first go. They just don't know what to make of it. It looks unbelievable. How can it fly? It's like the Twilight Zone.
Right, so what they have here is a large sphere which is rotating.
Frederick Purchase raised $4.5 million to test the concept of a very unorthodox airship. This is the 20-foot model of what Ferguson thinks is the proper shape for a helium-filled, lighter-than-air vehicle. Full-scale prototype, the sphere will be 180 feet in diameter.
We can have a sphere because it's the best container for the helium. It's a superb pressure container, and it's a lifting body to the craft. It has the controllability of a helicopter. It has the ability to truly hover, and its ability to turn is a great deal more sensitive and it's a great deal more tremendous than a helicopter. What makes a round fly is the fact that something that's round has to turn.
What's going on? I don't remember this video being so bad, but maybe it's just me.
Even more.
The spherical shape is a proven design. It's just not proven in aircraft. And that's what we're setting out to prove. We're not only proving a lighter than aircraft, we're proving a different form of aerodynamics. Well, if we're right, and the sphere can fly like a wing, and can control itself like the controls that apply to a helicopter, believe you me, this craft is just the beginning to a whole new era and a whole new configuration. It may lead all kinds of directions in the aerospace community.
Well, that's our report on the possible lighter-than-air technology of the future. No one can predict, of course, exactly if or when these modern airships might be available commercially. But if I still have the softness 5 to 10 years from now, it's just possible I'll be able to look out my window and see a lot more than just the Goodyear blimp fly by.
All right. So that's another example, all right? So there's this huge sphere here which is rotating to generate lift, making use of the Magnus effect. Now, as you can see from the video, that was many, many years ago. But now, in the future, you can see that we still don't have this kind of aircraft, right? Can anybody guess why a design like this, utilizing the Magnus effect, is probably not very practical? Going back to your lift and lift coefficient equations, can you tell me what happens when you have no uniform flow? Right? So if, let's say, you can see how slow the aircraft was flying, right? Or moving. And imagine if you have a gush of wind, right, in the same direction as it's moving, okay, basically then you're going to have a loss of lift, right, because your U infinity is basically just 0, right? Okay, or worst case, your free stream, your U infinity, is in the opposite direction. Then instead of having a lift in the correct upwards, you're going to have lift downwards, which I guess if you are a passenger in that plane, you wouldn't want that to happen. Okay, and here's also another example of, I guess, a wind turbine. Instead of having airfoil wings, you have a rotating cylinder to generate lift and supposedly be more efficient, but I guess that hasn't been the case. Okay, I have, I guess, one last video. Do you all have one? Do you want to have a look at another video? Okay, last one, a short one. Okay.
Questa è una punizione da vedere perché sempre sono da seguire le punizioni del piede magico di Roberto Carlos.
So this is, I think, in
Addirittura si prova da
1998.
di campo. Vediamo quello che succede. Il tiro. Splendido! Splendido gol! Fantastico gol di Roberto Carlos.
All right, so that was Roberto Carlos having a go at a free kick. Now, his, you can see that the ball is curved to the left, right? So lift is acting, well, there's a force to the left-hand side, right? Can anybody guess which direction is the ball rotating? Is it going to be in this anti-clockwise direction or clockwise? Anti-clockwise, right? Very good. Okay, so Roberto Carlos knows his potential flow pretty well. Okay. All right. Okay, so I think that's all for today. And tomorrow we'll enough of that music. Tomorrow we'll look at conformal transformation. Tomorrow will also be my last lecture. Okay, not for potential flow, but for me. And I will be handing out some revision sheets for you all tomorrow. Okay, so please come to tomorrow's lecture. Okay, all right, thanks.
Hey, can you do you know who has planned a team right now?
Oh,
Because I haven't found any yet.
have you emailed me?
No.
Oh, maybe send me an email. At the moment, I've paired up everyone. I think only you are left.
Yeah, because because the guy told me he wants
Another partner.
yeah.
Oh god. Yeah, I think everyone has a partner already at the moment. Yeah, but if anyone else emails me, right, then I'll pair them up together. So if you email me, and then if someone emails me later on, I will email both of you together.
So
But
your name is Sage A.
LZHCHAN.
Okay.
Yeah. Okay. All right. No problem. Okay.
I had a doubt. How can we understand that the lift is acting upwards or onwards, like, or the right or the left? Because you asked a question, right? The cylinder is there.
Yeah.
How do I understand that lift is acting on that side?
So remember, so So if you look back at this case, right? So flow is moving from right to left.
Yeah.
Okay, and it's rotating anti-clockwise, right? So here is going to have low pressure. Here's